Hi, my name is Zachary Burke, and I'm going to be introducing you to our NAE Grand Challenge project of developing energy through nuclear fusion. Fusion is the process which powers the sun and the stars. It is energy that makes all life on Earth possible. In order to replicate this process on Earth, gases need to be heated to extremely high temperatures of about 150 million degrees Celsius, whereby atoms become completely ionized. The fusion reaction that is easiest to accomplish is the reaction between two hydrogen isotopes, deuterium, extracted from water, and tritium, produced during the fusion reaction through contact with lithium. When deuterium and tritium nuclei fuse, they form a helium nucleus, a neutron, and a lot of energy. Due to the demanding conditions that are required to obtain fusion, scientists use a method called magnetic confinement fusion, which is an approach to generate thermonuclear fusion power that uses magnetic fields to confine the hot fusion fuel in the form of plasma. At the temperatures required, no material could withstand the extreme heat of the plasma. Magnetic confinement fusion attempts to create these conditions by using the electrical conductivity of the plasma to contain it with magnetic fields. There is another type of nuclear energy called fission, which can be seen on the left side of the Venn diagram, with fusion being on the right. Fission occurs when an atom with a very large nucleus is taken and neutrons are fired at it until it splits, producing a large amount of energy. Fission is used more prominently to obtain energy than fusion, due to fusion requiring a large amount of energy to produce the reaction and not yielding enough to make it a viable source of energy. Due to the small amount of data that we could find on nuclear fusion reactors, we decided to also include fission reactors simply to add to the functionality of our program. And now, Jacob will take you through the purpose and function of our program.
Hi, my name is Jacob Clare, and today we'll be going over our MATLAB script for our Grand Challenges project for Fusion. So, first part of our project is initiating a loop that makes sure that the program runs and will continue to ask a user if they'd like to run the program again and again, until of course they say no. Okay, so first part of the script loads our data set, defines the sizes and whatnot. And then the next part is data validation that checks to see if all the sizes, see if all the rows have the same number, see if all the columns have the same number, and will inform the user with a warning if it does not. That's all this. And then we have some data validation to make sure all the output values are positive, and if not, it will inform the user and ask for a new one. That's this for loop over here. So then, and this is just to check that all the capacity values are positive or if a value is missing. So then this is to calculate the capacity factor. It's the actual output of the reactor divided by what the reactor was supposed to make times 100 to make a capacity factor present, and that saves it into a vector called capacity. Then over here we have a little bit of statistical analysis, and our battery's running low. Find the minimum capacity value, the maximum capacity value, and the mean, and where they are in the matrix, and saves it to a 3-column vector. Here is where we check for reaction type. We have PWR, which is pressure water reaction, BWR, which is boiling water reaction, tokamak, which is a type of fusion reaction, says all that down here, Magnox, RBMK. And these are all just to check that the string matches one of those, and if it doesn't, then it's going to ask the user for a new one. Check it again, you get the drill. So then we are going to have a user select a reactor to view out of our list of reactors that's going to show up in a menu, on the left-hand screen over here. And this just makes sure that they choose a reactor. And then this is a formatted output statement of the capacities, minimum, maximum, and whatnot. And then we have the graph section, which I'll explain after we run the code. So let's run it. So here you see we have our list. We have JET, ITER, Anna 1, Fermi 2, Bradwell 1, Genk 3, Fukushima Daiichi 3, and Chernobyl. So just for example, we're going to choose ITER, and here we have our output statement. The ITER reactor has a capacity of 156.25% megawatts and uses a tokamak reactor that creates a fusion reaction. Minimum capacity is the JET reactor at 4107%. Maximum capacity is ITER at 156.25%. The average overall capacity is 95.04%, which is fairly good as far as reactors go. So then would we like to choose another reactor? Sure. Let's choose the Fukushima Daiichi. Fukushima Daiichi 3 reactor has a capacity of 100% and uses a boiling water reactor that creates a fission reaction. Minimum capacity JET at 41.07%, maximum capacity ITER at 156. Same as before, because it's the same data set. So let's say we decide to exit out of this. No. We should have a couple tables popping up, which is this part right here. There we go. Okay, so our first is a bar graph. As you can see, the capacity is in yellow and the output is in blue. And here it is for all of them. Reactor number, output, here it is. The battery is very low. There's that one. And then here is a graph of all the average capacity percents. We have a much bigger matrix of values that goes ahead and takes all of them and graphs them, which I'll show you down below. So here we load our data. Next couple lines looks like a lot, but really all it is just establishing bounds and values. That's all the maxes, minimums. That's for each line that I just showed. Is all that. That's title, labels, grids. Basically, all this just sets legends, output, everything you see on the chart, which we can show you again if we run. There you go. Choose one of these. Say we decided not to choose one, we're going to get a warning. Just to make sure you choose. So we'll say no, and then it takes a second. It's a lot of data. There we go. So there's our first chart, reactor number. See right here, reactor number, output, title, legend. There we go. There it is. And that is all. Thank you very much, guys. Bye.
Hello, my name is Tiffany, and I'll be adding on to what Jacob was talking about with our code. And so further, at the end of the code is our graphs. The one on the left is the capacity percentage, which our chart, the data that we used, had a very large amount of numbers from 99, so we had to break it up. And we didn't want to plot 99 points for each year. So we broke it up into the max values, the min values, and the mean values, just so you could see what's changing from that data. The data chart had 99 different values, and in our script we had to break it up into where it would run 1 through 50 and then run 50 to 100 because it was just so much that MATLAB could not handle it. So it took about twice as long to code it. We added the lines just so you can see the change from year to year and the from it increasing and decreasing on the capacity percentage. On the chart on the right is our nuclear data chart bar graph, so you can see each reactor number and you can see the output from the megawatts and the capacity for the megawatts for each reactor. No matter which one you pick in your menu, it will show you all of them just so you can see all the reactors that are in our chart and from the data sheets that we provided from online. I outputted it as a bar graph because I thought it would be better reading so that you could see the changes from each reactor and from each output and capacity percentage. Thank you for watching.